Net ionic equations. We only write net ionic equations for double displacement reactions, and to be able to do these, we first have to predict our products, and then we have to use a solubility chart to determine the product solubility, either solid or aqueous. We're going to then separate any of the aqueous ones into their ions. We cross out ions that are the same on both sides, and whatever we have left is called our net ionic equation. So let me demonstrate that for you. So the first equation is called a molecular equation, and this is when we have everything written. We have the reactants, we have the products, and we also have the phases written for our products. And we want to make sure everything has our phases. Nothing is separated, it's just a full reaction. The next step is then called the complete ionic equation, and this is when we separate just aqueous. Now, a tip that I've found over the years is students will kind of get caught up in separating. So the one that is the solid, which is the precipitate, that is the one that I like to box off. And I just find it helpful because then students kind of notice that it's one that you're not going to keep separating. You only separate aqueous. So we're only going to separate this one, and this one. Okay, that solid stays together because aqueous breaks apart into ions, solids don't. So let's go ahead and write this. Now, another thing you need to keep in mind is this coefficient. Coefficients go to both things, the metal and the non-metal. So when we separate K and OH, I'm going to go ahead and just do this up here before I write it down below. And then the Mg is a +2, and we know NO3 is a -2, or -1, excuse me. And then we know that K is a +1 and NO3 is a -1. Now I'm just breaking this part up here to show you how to do the complete ionic. So what you're going to do is keep them separate, but you need to take into account this coefficient. So this becomes 2 Ks plus 2 OHs. Ions, of course, not just K, it's K plus, and not just OH, OH minus. So that 2 goes to both when it's a coefficient. Now, Mg is a +2 here. There's no coefficient, so we don't have to worry about that. But when we have a subscript, which you can see the 2 here, that also gets brought up. So it becomes 2NO3 minus. So two things can become a coefficient in our complete ionic. It can be the coefficient in front of the actual, ionic equation, or it can be a subscript. So this 2 here breaks apart into, let me go ahead and make this an arrow. You bring your arrow down, of course, and it becomes 2K plus, 2NO3 minus. And then, as I said, it's easy to kind of get stuck with separating everything, so I like to box that off to remind myself these do not separate. Now, a good habit is to go ahead and continue writing all the phases. So I'm going to go ahead and do that. I kind of forget about that sometimes, but you want to make sure that you know these are all aqueous. You do not separate liquids. You do not separate gases either. You only separate aqueous. Now, the net ionic, we're going to find that, we're going to cross out everything that is broken apart on either side. And when I say sides, I mean the arrow. So I see 2 Ks, and I see 2 Ks here, and I see 2 NO3s. I see 2 NO3s. So what I'm left with here is the 2 OH minuses plus the Mg +2 yields my Mg OH2. Okay? So that is my net ionic. That is basically what the important components of the whole reaction are. Doesn't mean the other things don't exist. It just means that they're not as relevant. They're not creating that soluble or the unsoluble product or the precipitate. Now, the things we cross out on both sides are called spectator ions. So think about it as like you're a spectator in a sporting event. You are there, but you're not participating. So that's how you need to think. So the 2 spectator ions in this are the K plus ones and the NO3 minus ones. Okay, 2 spectator ions in this reaction. And spectator ion here is described an ion in an equation that does not take part. Okay, and it has to be a reactant and a product, and we cross it out. So again, here is the another example. If we had the reaction of BaNO3, there's 2, plus K2CrO4 yields BaCrO4 plus KNO3. And it looks like the solid one is this one. Everything else is aqueous. So what we did here was separate the aqueous. Remember to take into account the coefficients and all that. So the 2 here can be seen in front. The 2 here can be seen as front as well. Okay. And you can see that 2 here, because you need to balance the equation. You always want to balance as well when you're working with your first equation. Now the ones that we're crossing out here are the NO3, the Ks. So again, we have our net ionic, and the spectators are the Ks and the NO3s in this instance as well. All right, so decide whether the following reaction occurs. If it does, write the molecular, ionic, and net. So let's go ahead and see what we're working with here. Let's go ahead and predict your products. This becomes NaCl. This becomes MgOH2. Okay? So when we go ahead and look at our products, NaCl would be aqueous because it has an Na, which is a group 1A, and then this one's going to be a solid. So as long as it's not too aqueous, it does exist. So let's go ahead and balance it, and then let's go ahead and write our complete and net ionic. So I have 2 OHs here. Go ahead and put a 2 there. All right, so let's separate. And again, you may find it helpful to write them up here. You do not have to. It's just demonstrating how that would work. So 2 Na plus 1. I like to always box this off just to remind myself to not be overzealous with the separating. This is aqueous. This is aqueous as well. And the Mg is a plus 2. And then we have 2 Cl minuses. Remember, this 2 is 2 places, in the 2 here and in front. Okay, so subscripts are seen in 2 places when you are separating. And coefficients are also seen in 2 places. And I'm just going to go ahead and bring this down. You just bring any precipitates down. All right, now go ahead and cross out your spectator ions. Again, those are the same that are on either side. 2 NAs. Now they have to be the same coefficient as well. So if you're not getting the same coefficient, you probably screwed something up when you were writing your equation. So always check that out. And then we're left with 2 OH minuses and 2 Mg plus 2s. Gives us, oh, I didn't mean an equal sign. I just want an arrow. MgOH2. Solid. All right, let's go ahead and do this one. Write your products. Try this one on your own. Pause the video, and then you can check your answers. So I'm going to make this a 6. And this a 3. I do want to show you how this one's actually probably the most difficult out of them. When you are taking into account a subscript and a coefficient, you actually would multiply these for your coefficient when you're breaking it apart. So it becomes 6 because there's a 3 and a 2. And this 2 then also goes to the PO4. Okay, and this is the solid. I should have written that before. And this is my aqueous. So again, you can't do this without it being balanced and having all your phases. So this is my precipitate. Now, the boxing is not required, okay? It's helpful. I found it helpful over the years. You don't have to box it off. It's just something that's worked. That's another 6 in front of the CL. Again, it's 6 because you have a 3 and a 2 here. So I have to cram this in here. Go ahead and cross out your spectators. And they both have 6s in front of them, so you always want to make sure that they are both the same coefficients and ion charges. And then what I'm left over with is 2PO4 minus, excuse me, I'm looking at a small mistake that I occurred before, and I apologize about that. It should have been a 3. PO4 minus 3 is phosphate. So I will tell you, this is about as hard as it gets, is this problem when you're separating them. So you have to take into account charges and balancing coefficients. Okay? So if you got that one, you've understood. So let's go ahead and predict these products and see what we're working with. So the outers are joining, the inners are joining. This becomes K2SO4. Remember, sulfate is SO4 minus 2 in MgBr. So take a moment and go ahead and look at your solubility chart and figure out what the phases are. So we have aqueous here for potassium sulfate, and we also have aqueous. Now, as I reminded you above, 2 aqueous do not make a solution. So when you're left with 2 aqueous products, it's actually no reaction. So we do not have to do a net ionic equation because everything would be spectator, okay, because everything would cross out.